So, welcome to another interview for the Zero to ASIC YouTube channel. And this week, I'm very happy to be joined by Jason Blocklove and Dr. Hammond Pearce to talk about their recent paper about using AI to design chips. So, how are you both doing?
Doing well. Doing really well. Thank you.
Yeah, so maybe we'll just start off with a bit of context. You can tell us a little bit about yourselves.
Sure. Yeah. My name's Hammond. I'm a research assistant professor here at New York University. I'm actually about to head over to the University of New South Wales in Sydney, but I'm just finishing up my contract here at the moment. And my specialty over here has actually been in sort of the hardware security domain, but a huge part of that over the last few years has been this kind of explosion of AI that's being used and applied to hardware, particularly by people with the same interests that we do in our research group. And so Jason is a student that has joined during my time here, and he's also been involved with it.
Yep. Yeah. So I just finished up my first year of my PhD, primarily working on, I guess, a bunch of things in hardware security. But yeah, the most recent effort has been with trying to use large language models and AI for generating hardware.
Okay, so how does generating hardware with AI relate to hardware security?
So the big thing for us is that we know tools like GitHub Copilot are going to be used by everyone, right? And it took precisely about 5 minutes after I got Copilot access before I was like, hey, I write a lot of Verilog. Can I write Verilog with GitHub Copilot, right? And we're not the only people with that thought. But the thing is, the way that GitHub Copilot works, right, is it's trained over a lot of open source code, and the open source examples of Verilog sometimes aren't super amazing. If you go on GitHub and you look at people's designs, some of them are great and some of them are not so great. And the problem is the model can't differentiate between what is good and what is not so good. And so what might happen, especially if you're an inexperienced hardware designer, is you're going to rely on what GitHub Copilot and the other tools suggest to you. And so, yeah, that has serious implications, because if they suggest to you bad things or code that is problematic from a security point of view, you might not notice that. If it suggests to you code that doesn't work from a functional point of view, people do normally notice that the thing's not functioning, right? Like ideally you're testing your designs, but testing for security is a lot harder. And so that's really where the angle that we've come in on this is, because it is difficult to test for security. If you don't understand the implications of what's coming out of these models, you might end up importing bad practices and security mistakes into your designs.
Right. So how long have you been interested in using AIs to generate Verilog?
Yeah, I've been doing it for about as long as I can. So I started back with GPT-2. The very first work that we did was back in 2020, and we trained a model that we called Dave to produce Verilog over, a very small amount of examples. We were just training it over undergraduate student work at the time, and actually, like questions from textbooks and things like that. And it wasn't very good, but that was fine. And then we kind of put it on the back burner until GitHub Copilot came out, and we were suddenly like, wow, overnight these models have gone from being sort of okay at maybe writing something that vaguely looks like code to already like, wow, it can complete whole functions in languages like Python and have a decent pass at completing modules in languages like Verilog. And so that was what really caught our interest again. And because we'd done that foundation with the earlier model with GPT-2 and Dave, we already had a lot of understanding of how the models worked, what they were trained over, and sort of the kinds of ways that we could evaluate them. And the interest, a little bit of expertise. And how did you get involved with hardware, Jason?
With hardware in general, it goes back a bit further, but specifically for using AI and LLMs to generate hardware, it really started when ChatGPT 3.5 got released. Hammond and my advisor, Dr. Kari, both got very excited about it very quickly, and suddenly I was asked, like, hey, can you try to make this thing, generate a basic shift register and generate such and such. And GPT 3.5 was bad at it, to say the least. It was impressive how well it was doing, given that we, didn't have a whole lot else to go off of. But sometimes you'd ask it to make a state machine and it wouldn't even make anything that even looked like Verilog, let alone anything actually functional or synthesizable. But then we started poking at it more and more, and then GPT-4 came out, and that kind of kicked off we can actually get this to make stuff and make stuff that
Yeah.
works.
Yeah. Yeah. So maybe we can just bring up your paper now, and for people following along, we'll put a link to the paper in the description down below. It's a really good paper, very accessible. Um, so maybe you can just give us a little overview on this. What's happening then? What was your
Yeah.
methodology?
Yeah, of course. So the paper is called Chip Chat. Oh, you scroll up a little bit, it'll show the title. Chip Chat, Challenges and Opportunities in Conversational Hardware Design. And it really was this kind of idea of, we know that these language models are now out. And we already kind of knew that they could generate hardware from, if we go back to GitHub Copilot and the earlier like GPT-3 and Codex models, they worked on a kind of autocomplete basis, right? You give them some code and it sort of continues the code. But for the first time with ChatGPT 3.5 and the other instruction models, Instruct GPT and then Hugging Face Chat and Google's Bard, and now there are other ones as well that are coming out, and they're trained not to necessarily autocomplete things, but to actually, in many ways, have a conversation with you, right? So sometimes they're called instructional models because that was their basis, but they're more like conversational models. And if you go on ChatGPT, you can have a conversation with it, right? And so we thought, well, that actually kind of fundamentally changes the paradigm a little bit, because instead of now really being in the driver's seat and writing everything and just getting suggestions, now you're really making requests of the model and say, hey, finish this off, or maybe there's a bug here. Can you correct the bug and things like that? And the models can comprehend that in a way that they weren't previously able to. Now, our interest came into this because, again, people are evaluating these models primarily for software, right? The vast majority of the work that you go and read, it's evaluating the models usually over Python programming. But Python is Python and hardware is hardware, and there's attempts to join them. I know you're a big fan of CocoaDB for testing, but for the actual design itself, we tend to rely on languages like Verilog still. So we thought, well, let's try and come up with a systematic way to evaluate these models specifically for Verilog, kind of like how we've done in the past with the other simpler models, but also trying to take advantages of the unique things that a conversation can give you, where you can have a back and forth with the model, where you're not just reliant on a single suggestion or collection of suggestions, where you can actually, build a timeline of your conversation through. So that's really what we were exploring here was, can these models even do it yet? That was our fundamental question. Can we actually do this? And as it turns out, yeah, we kind of can, and to greater or lesser strength. So Jason led the initial experimentation phase. So if you want to talk a little bit about that, that was where we kind of tried to do it in a more structured sense. So I'll let you take over.
Yeah. So
there's a place in the paper, isn't there? Where
if you scroll down to Figure 2, it's a good flowchart for that.
Okay.
There it is. So the initial kind of goal with that was, can we give an initial specification to this LLM? We ultimately tried 4, although, as I mentioned earlier, ChatGPT 4 was kind of the only one that had reasonable success. But can we give a prompt to this large language model based on just initial specifications? So generally speaking, it was, what are our inputs and outputs, and a vague description of how it's supposed to work, and have it go all the way through making the design, making a test bench, correcting the design based on feedback from tools. We used Icarus Verilog for all of our simulations because open source tools are always, fun to use, and it was relatively simple to have it make test benches for. And feedback, all this tool feedback, until eventually we got theoretically a functioning design. That didn't always work out quite the way we wanted to, which is why we've got these branching paths in the flowchart there of, the initial errors, we just give it the feedback from iVerilog. We just say, hey, we got these errors, please correct them. If it couldn't do that, I would give some level of simple human feedback. There seems to be an issue with the syntax of your parameters in this file or something. If it still couldn't fix that, we'd go on to moderate feedback of, this parameter has incorrect syntax, please fix it. And then advanced human feedback is saying something along the lines of, this is where the syntax is wrong, this is a general idea of how to fix it, up to the point of, if I had to give actual Verilog saying, this is what would fix it, we consider that a failure. At that point, at that point, it's no longer doing the writing of the Verilog.
Mm-hmm.
So that was the initial set of experiments was, can we keep this as insular of a loop as possible and have it just purely create both the design and the verification setup for that design?
Yeah, and so that's something, a point I want to make is in this work, we didn't write any of the Verilog. The only thing that we wrote was the specifications for these initial experiments, and we got ChatGPT to actually write its test benches itself, because that was a big part of this is we really want it to be so just there figure 4 is once you've got the design, can we actually now get the tool to make its own test bench to actually test its own design. One of the main findings from that, though, is that actually it's not nearly as good at testing as it is at writing. We've got some theories about that, mainly to do with the availability of open source. All of these models are trained over just open source examples, and open source designs don't have, not very many of them have really well-made, super comprehensive test benches. And even when they do, a test bench is so tightly coupled to what it's testing that it's difficult to generalize that knowledge, right? I could show you 100 test benches for 100 different designs, but if you don't really know the theory of what's going on, trying to come up with a test bench for 101st design is still going to be a very difficult task.
Yeah.
So based on what we learned from that first set of experiments, which is that functionality was pretty good with ChatGPT 4 and maybe not so much the other models, and the test benches were kind of middling for all of them, we thought, well, okay, let's take the strengths here. And the strengths is that ChatGPT 4 is very good at writing functional code. So we said, let's make a harder design. We'll have it unstructured this time. We'll just rely on human feedback the whole time. And we'll try and make something big. So we big but limited by our new constraint, which is that we just learned out about TinyTapeout. So we thought, hey, let's make something that, that pushes the model to its limits, but can still fit within the constraints of TinyTapeout, because that's now really interesting. That adds another flair and another challenge to the design task, because now you have real world design constraints in that, I said, I want to make a processor. We go, okay, we have to fit a processor into TinyTapeout 3. That's not a lot of space, right? So now not only are we making a processor, we can't really make a processor like all the other ones that are on GitHub, because they're just straight up not going to fit on TinyTapeout. So I'm a computer engineer. I went, okay, let's go back to 1970s computer architectures, right? We'll do an accumulator-based design. They're really small. We'll cut out as many features as possible. We'll make it 8 bits, and then we'll see if we can fit that into TinyTapeout. And so that's what we did. And the next part, if you scroll down a little bit more, we said, okay, the strengths are here's some great that figure on the right with that was Hugging Chat trying to write the shift register. So you can see Hugging Chat not quite so good at writing Verilog as the other.
I think the synthesis tools would choke on that.
Just a little.
Yeah, my favorite is that it says grandpa in the middle. If you take a look, super helpful. But so scrolling down a little bit more. Sorry, I got distracted when I saw that. It's just so great. Yeah, so keep going.
Those are the benchmarkers.
Yeah. So here we go. Free chat. Yeah, so here we go. So you can see my prompt there up on the top left and figure whatever it is, figure 10. So you see that it says, let's make a brand new microprocessor. We're constrained on space and I/O thanks to TinyTapeout. We have to fit in 1,000 standard cells. So we're going to restrict ourselves to an accumulator, right? And so I let, in many ways, ChatGPT actually tell me what to do, and then I gave it help as well. So it said, these are the steps to design a computer processor. You need to make an ISA, then you need to make components, then you need to wire the components. And I was like, great, that is the steps to make a processor. So then that's kind of what I did. So I shepherded the model to try and come up with its own design, back and forth. And then I tried to preempt mistakes that it made. So if I saw it was making a really bad choice in the ISA, I would say, don't do that. Or, when it made the branching instructions to begin with, the first attempts were just horrible. Actually, it bamboozled me. We had to go back and fix them later, which, so in the conversation flow map on the right there, we broke up the topics for each part of the process of design into a number of different threads on the ChatGPT interface. And we did that because these models can only ingest a certain amount of information. Right? They have a fixed amount of what's called their window size or their context size, which is the amount of I/O or the amount of text they can comprehend at any given time. It has a finite limit. Now, they don't actually say what that limit is for ChatGPT, but we can guess because we know that their previous sort of model they talked about was GPT-3, and that could handle about 8,000 tokens, which is about, what is that, about 24,000 characters or something like that, right? So it's not a huge amount of text. So as the conversations got longer, we tended to just cut them off and then start a new conversation. And I would copy and paste in just what we needed for that specific conversation to get it started again. So you can see that the first conversation, we did the specification. That was the ISA, right? So I made, back and forth over the course of, that says 22 messages there. We built all of the instructions that we would need to actually make the processor work. And then after that, we then made the registers, and then we made we specified the registers, which registers we need, then we made them, then we started planning what was going to happen in each clock cycle, and then we planned out what control signals we would need. And eventually we then wired it all together, and I actually got it to make its own assembler for it. And you can see that only took 3 messages, because again, these models are so much better at Python than they are at anything. I just gave it the ISA it made and went, write me an assembler, and it did it in a single pass, basically. I was like, wow, okay, cool. And then once we had the assembler, then I could actually start to test it, right? And so this is where I started writing code again. I did make the test bench for the processor because I knew that it was not very good at making test benches. So that was the one thing I made, was the test bench. And then using the assembler that it made, I wrote some small programs. And you'll see the very first thing we did was I went back and was like, oh no, there's a terrible mistake to do with the branching logic, because we just can't branch the number of instructions we need to branch to achieve anything. So I had to go back and change a whole load of stuff, which we then did by kind of going back to the conversations we'd already started and saying, okay, I've done testing, the branching doesn't work very well. Let's try and fix this. And eventually we ended up with a full design. It took 125 messages to do it, but it was actually remarkably quick. I think all up, 125 messages to build a whole processor is short, right? Like, if you imagine that each message sort of takes maybe a minute, that's 125 minutes. Of course, it's not, because ChatGPT has some crazy rate limiting, so you can only do 25 messages in 3 hours. But, realistically, if that wasn't there, you could imagine that I've built a whole processor in just a couple of hours with the help of AI. And that's not just a processor that exists before. This is a whole brand new processor with a brand new ISA, which is bizarre enough that I don't think anyone else would want to make a design quite like it. But the point is that, this is such an enabler. And that's, to me, the power of this new AI stuff, is it's such an enabler and a force multiplier for engineers in this and other spaces.
Mm-hmm. Yeah, so I was just chatting with somebody earlier, and they said, as far as I can tell right now, it's just throw spaghetti at the wall and let the human figure out if it's any good.
Yeah.
So is that how it's been in your experience? And maybe we can dig into the verification side of it a bit, because I think if I was doing this, I would be very worried that it would include some bugs that, it's very difficult to get high test coverage anyway, even if you've written your own design. So how can you ever really trust what's coming out of these models?
Yeah, so we ran into that a lot, especially with my tests, because I had it create those test benches where the coverage was generally very poor. There were a number of cases where it would actually just have a comment in the middle of the test bench saying, add more test cases here, expecting the human to do that, because I think to a certain extent, it knows as much as it can know.
Well, it's learned that from somewhere, hasn't it? It's learned it from... It's read all these open source test cases where someone's wrote a note to themselves in the future, must add more tests later.
Yeah.
To do.
But yeah, we ended up running into a number of issues. One of them was with that test coverage thing. I mentioned this before, but the dice roller benchmark. I made a benchmark that you select one of 4 different types or numbers of sides of a die, and it rolls a random number for you. And the one that actually made it on TinyTapeout, the first one that I ever tried, the test bench says that it passes. I had it make a self-checking test bench. It would report if it passed all the tests. It reported that it passed all the tests, but the thing it tested for was just, is the number that it rolled within the bounds of the number of the sides of the die? So if you're rolling a 5-sided or 4-sided die or 6-sided die, is it between 1 and 4 or 1 and 6? It always rolls a 1. It's just it rolls a single 2 because there was a bug where it wasn't where it was rolling a 0 to start with. So now it rolls a single 2 and then ones, no matter what you put into it. So it's a big issue of, if you're a new designer who doesn't understand testing very thoroughly and things like
Yeah.
that, and you just trust that this test bench says that it passes, suddenly you have a design that absolutely does not do what it's supposed to do. But because the AI wrote this test bench that says it does, you just end up taking it at face value. And another problem we ran into a lot was with any of our designs that involved state. So there are a number of state machines in those tests. One really good example is a traffic light controller. So it just sits at, it outputs a red light for, I think, 32 clock cycles, and then a green light for 20, and then a yellow light for 7, I think. And it does a very bad job keeping track of what state it's in the testing. So it ends up saying like, oh, well, I just finished red. Now the next correct state must be yellow. And well, no, that's not how a traffic light works. So again, it eventually kind of worked through some of those issues, and it was better at fixing the problems with tracking states than it was at fixing just general test coverage issues. But it still ran into a lot of these problems where if you're not a hardware designer, you don't really understand how to fix them.
Yeah.
Yeah. So, go ahead.
Okay, so this was the Qt Challenges one. So if people want to look a bit closer at these designs, obviously they're all on the internet.
Yep.
And here you can even see the
prompts. Yep, all of the prompts are included. In the GitHub itself, there's a folder for the conversations that has absolutely everything put in Markdown. And then the documentation includes, in some cases, includes both the expected functionality and what it actually does.
Yeah. Okay.
Yeah.
Fits easily, this one.
Oh, yeah.
Yeah, that one wasn't quite such a struggle like our like the full processor design was.
Yeah, the benchmarks are nice and small.
And then this one is the processor.
Yes, so this is the full processor. There's actually 2 versions on TinyTapeout because we had another PhD student who did an additional experiment using the processor once it was built. But yeah, so you can see everything here and all the designs. And I actually did test it in addition to in simulation. I put it to an FPGA and we tested it on an
that's
FPGA
a good idea.
as well. That's why it's got a little bit of C code in there because that's what I used. So getting it to fit was a bit of a challenge.
Yeah, 60%. Congratulations. Yeah.
Yeah. It was a bit of a chore. You can see it's a bit tight. I got ChatGPT to parameterize the memory space so that I could easily from the top level file, which is kind of like the wrapper, which I excluded from its authorship. Was all I did was change the parameter size in there and just kept reducing the size of memory until it would fit, basically. But yeah, so it was a bit of a challenge, but it worked pretty well in the end. And we were generally pretty. I've been working with these models for a while, and to go in like 3 years from struggling to write a basic flip-flop to fully architecting a processor is pretty impressive. And I'm very interested to see where it goes in the next 3 years.
And then taping it out. So is this, do you think this is the first AI written core to be taped out?
Yes. Yeah, I do. We've asked around a little bit. No one can say for sure, but we've asked quite a few people that we feel like are at least adjacent to the field. And so we're pretty confident in saying that, we believe this is the world's first AI written hardware for tape out.
You're welcoming in our new AI overlords.
Yep.
Yes. Okay. So, what else do you want to talk about? Maybe you can tell me a little bit about your plans for the future.
Yeah. So in terms of career-wise, I'm obviously about to head over to Australia. Actually, my Australian email and contact is already on the paper, in case you're confused, because it doesn't say New York University, even though that's where I introduced myself from. But yeah, in terms of research, I'm super excited to continue working with these models to try and address the weaknesses that we've identified that, it's still not so good at verification and testing and that sort of thing. We want to make the models better at that because in many ways, that's the bit that they can be most useful at, actually. testing is
Yeah,
hard.
no one likes writing test benches, do they?
No one likes writing testing, and testing well is hard. It's a properly difficult skill. And if you have a look at the you look at the design process flow for real world chips, and you talk to Intel, and they'll say they spend 10 times the amount of design time on verification, because it's so critical to get right. And there's so many things you need to check for, not just from functionality, as I brought up. You do also need to check for security properties if your code's ever going to, or your design is ever going to be doing anything related to any kind of critical task. So having AI that might be able to guide you and maybe even teach human engineers how to do that testing, it's going to be a big force multiplier for engineers that know what they do, and a kind of democratizing force, hopefully, for people who don't know what they're doing. But of course, the challenges right now is that, the models are not super competent. And so, I'm comfortable in saying, I'm a hardware engineer. I can sit down with the model and, get a chip done really quickly because I can see the mistakes it's making. Jason can do that too. Although with Jason, we didn't let him tell him.
Yeah, I didn't get the chance.
Yeah, there's no feedback loop in there for Jason saying it's bad. But yeah, no, so the thing that the point that we're trying to make with the early experiment is, Jason was pretending he didn't know what he was doing, and so as a result, as we said, we're taping out a dice roller that doesn't work because that was the kind of the goal of the experiment. We go, Jason's pretending he doesn't know what he's doing, and as a result, no one caught
these are the kinds of results you might expect. Yeah.
Yes. Yeah. And so, whereas you pair it with a more experienced designer, you can get something along the lines of the second experiment, which was, we got a processor out of it. So what we want is for the second experiment results to be more like the first one, where you can give it the model to someone who doesn't necessarily know what they're doing, and you say, hey, how do we make a processor? Okay, let's now do these steps together, and not need to worry so much about the mistakes that the model might make.
Great. Well, thanks very much for sharing your knowledge and writing the paper. For people that want to get in touch and find out more, they should email you on the links in the paper, I guess.
Yes, yeah. Our email addresses are just at the beginning, and the paper is on archive, so it's freely accessible. You don't need to worry about paywalls or anything like that.
And we'll link that down in the video description. Great. Well, thanks very much again for your time, and have a great rest of your evening.
Thanks. You so much. This was a lot of fun.
Yep.